nucleus, there's a magic extra special force which only acts on very short distance scales, very weeny distances, which is called the quantum theory of chromodynamics, or the strong force that binds the nucleus together. And it does it with little particles that physicists have called gluons. This is very imaginative. It just indicates that in order to glue the protons and the neutrons together so the nucleus doesn't like explode and make our bodies go boom, there must be a strong force that acts only on the nucleus that keeps that nucleus nice and compact and all together. It must be so strong that it can overpower that electric repulsion between the proton, the neighbors inside the nucleus. So that's just one example of how thinking harder about the physics of really wee things can give you some stuff that's a bit counterintuitive. I mean, so that's the reason why the atomic nucleus doesn't explode, is that inside the nucleus there's a strong force which is pulling those protons and neutrons together far harder than the electric forces pushing them apart. So what would happen if you looked inside the protons and the neutrons inside the nucleus? Well, something that physicists discovered, I guess over 25 years ago, is that inside there's these little hard thingies called quarks, and apparently for the name of this came out of some passage of Finnegan's Wake. 3 quarks for Muster Mark, or something like that, and so they decided forever and ever amen to call the little particles that make up protons and neutrons quarks. At any rate, there's these teeny weeny things, and 3 of them live inside the proton, and 3 different ones live inside the neutron. And so these quarks make up the subatomic particles that make up the nucleus, and they're thought to be elementary. We don't see any subquarks inside quarks or anything. So to the distance that we can currently look, which is about 1/1000th of a billionth of a meter across, we think that inside the nucleus there are the electrons which whiz around the outside, and then there's little quarks that help make up the protons and neutrons that make up the nucleus. So I've just given you a whole third-year physics course on nuclear physics and stuff like that. And I know it's a bit ludicrous to try to describe it in 5 minutes, but that's what we've just been talking about. That if you look at the structure of matter and stuff, if you looked inside, the neutrons and positrons and the electrons and stuff inside the band-aid on the thumb that I managed to cut with a very bad knife a few days ago, then this is what you would find inside. You can't keep chopping up the nucleus. What you get are these hard little elementary particles in the middle that make up the nucleus and the atoms that we see in our bodies. So physicists, having studied and studied and stared at the physics of very wee things for very, very long amounts of time, decades and decades, we know that we know that there is these hard little elementary particles that live inside the nucleus and make up the electrons and stuff that go round and round and round. But here's something that's even weirder about the physics of very small things. And please, by the way, don't be frightened by what's on the... Again, this is just a memory for me to remember what to say. I won't explain most of it by what's going on. But what happens in the micro world is that there's something that doesn't affect us when we're living in the macro world. For example, if I've got a human or a planet or a dog or a hockey puck, the physics that I'm going to describe, which is called quantum mechanics, it's something that was discovered in the 1930s. And what it says is, in the microscopic world, things are not as definite as you thought they might be. In fact, elementary little subatomic particles, like an electron or a quark inside an atomic nucleus, it has what's called some uncertainty about it. It sort of has this jitter, and it's a bit fuzzy. So it's not very definite about where it is at any given time, and it's not very certain about how fast it's going. It's got some rough sort of average properties, but there's a bit of uncertainty about what it's doing. And this fact that little subatomic things are a bit fuzzy, they've got this uncertainty about them. You can't really know too much about where the particle is and how fast it's going at the same time. This what's called quantum weirdness. There's aspects of the fact that sometimes these little subatomic particles appear to behave like pointy things, like particles, but occasionally, if you do the right experiment on them and look very hard, you can see wave-like properties of electrons as well. And so you may have seen in popular descriptions of this, words like, well, there's this thing called wave-particle duality and blah, blah, blah. But I find that the least confusing way to talk about it is to say that particles are how it appears to be sometimes, and sometimes it appears like an electron can behave in a wavy fashion, but in real life, particles are wavicles. Subatomic objects like electrons are really wavicles. If you look at them in the right way, they can behave like waves. If you look at them in a different way, they can behave like particles. So I just prefer to call them wavicles, because that's less confusing. And many of the students in my class try to use this word and when they write exams and so forth, and I tell them, well, it's fine if you write that in my exam, because I know what you mean, but just be aware that other people don't necessarily use the same terminology. At any rate, let me just ignore that for the moment. What I mean to say is that what the laws of quantum physics tell us, and this is something that you can only learn by looking at the really small, the physics of microscopic things, the physics of very small things, is that there is an essential uncertainty about things at the basic level. For example, an electron, you can't necessarily pin down exactly where it is. It's like it's a small, 2-year-old child who you can never stop from moving, and you're never sure where exactly it is at any given time because it's moving around, and it's got too much jitter to it for you to be able to say, hey, stand still so that I can measure where you are. So it's like these little subatomic particles have a basic jitter about them, like they're 2-year-old and excited all the time. And what the message is about this is that this jitter effect is stronger the smaller you are. So very small particles, very small subatomic particles have this, what's called this Heisenberg uncertainty to them, or this quantum mechanical uncertainty. But again, the quantum effects are stronger the smaller you are. So if you're a really, really tiny subatomic particle, then this quantum jitter effect is going to be a rather large feature of your life. I mean, you're not really going to be able to ignore the fact that you can't stand still and so forth, and you're sort of like trying to behave like this. But the story is, supposing we asked what would happen if I were large. Suppose I were the size of a human being, like an Amanda particle, instead of an electron. Suppose I was going to compare the behavior of an Amanda-on to an electron. Now, you all know perfectly well that the Amanda-on particle standing in front of you is, it's definite where I'm standing. There's no quantum uncertainty about what's happening to me. And I also know that if I stare at my laptop, I know exactly where it is. There's no uncertainty. Like if I go like that, I'm going to press the right button. It's not that the laptop is going and moving around. So how can it be that very small things have this uncertain, this jitter to them, while very big things don't have any at all? Well, it's just that, again, there's this rule that comes from quantum mechanics, and you can work it out from first principles if you need to, but you can just go and look in experiments and see it too. That again, the quantum jitter effect is bigger the smaller you are. So it affects subatomic particles, really wee things, in a big way. But if I'm talking about an Amanda-on, who is perhaps, let's say, about a billion thousand times heavier than an electron, then because I'm so much bigger, the jitter effect is a very tiny little effect. So there is a jitter effect, a quantum jitter effect, that makes my position uncertain. But the uncertainty in my position is very small, so small that it's unmeasurable. And so big things behave in definite ways. That's called classical physics. That we have definite positions, we have definite velocities, we go at a particular speed. If you know enough information about us, you can predict what we're going to do in the future. And there's no uncertainty or any jitteriness or, like weird stuff happening. Things behave like planets and pucks and, humans and stuff. So it's only when you get down to the physics of very small things that they start to have this jitter about them, this uncertainty. And that, in a nutshell, is what the physics of quantum mechanics is about. Yes, there's some weird things that sometimes an electron can behave more like a wave than a particle, and that it doesn't have a very definite position. If you try to look at it by firing some light at it, it sort of knocks the electron off course. Just the effect of a little light particle bouncing off the electron is enough to bugger up its plans so that it changes its course and so forth. And sometimes people express that Heisenberg uncertainty as saying, if you try to look at something, then just the act of looking at it makes it not very definite where it is. And again, that's just because to look at something, you have to fire some light particles. You have to look. You have to poke it somehow. So at any rate, this physics that arises from looking at very, very small things can give rise to some slightly unexpected results. But what I just wanted to give you a sense was that classical physics, the stuff that was around before 1930, Newton and Einstein and all these incredibly famous people taught us how to do that physics of very large things, and then positions and motions and so forth are definite. But there are different rules that apply once you get down into the quantum world, the microscopic world, that things are not quite so definite anymore. Things are a bit wafflier, a bit more jittery, and it's harder to pin stuff down. And that complicates the physics of how we look at the physics of the very small. But let me just talk a little bit more about particle physics, because it motivates why you would bother with strings. After all, I've said, well, there's all this beautiful knowledge about particle physics. Why would we even bother with the idea of having a string? Well, it turns out to solve a number of problems that you can't solve just by having particles. So, you know, again, ignore the words and so forth there if you choose to. But if you were starting fresh and wanted to know, how does a physicist tell different particles apart? I mean, after all, if I were a particle physicist and I were in a lab and I were looking at, you know, my little experiment and I was seeing flashes of light or whatever it is that I was looking for, how would I be able to tell an electron apart from a quark? Or how would I know that there was a particle of light? A photon, that's the name of a particle of light, little bzz of light energy, that's called a photon particle. And how do I tell the difference between different ones? After all, if I'm going to have a theory about my elementary particles, if I want to understand all the particles and all the forces over those massively different distance scales, I'm going to have some way of saying, well, you're an electron, and you, sir, are a photon. But I need to know how to tell the difference, after all. So if I'm a physicist, how do I tell different particles apart? Well, it turns out that there are only two ways of characterizing particles that physicists can agree on. So, and people express that in physics words by saying those are the only two ways of labeling a particle that are invariant under the symmetries of space-time. That's just fancy language for saying that if I'm, say, doing measurements in my lab, and I'm in Montreal, and you happen to be doing experiments in your lab and you're on Mars, well, just because we're separated by some distance, we should still pretty much see the same thing. I mean, no matter whether I'm in Mars or you're in Montreal, we ought to be able to agree on how to label a particle. Because after all, if our answers depended on which way we were looking, that wouldn't be a very sensible way of labeling particles. So this is just sort of common sense. It says, well, let's pick ways of characterizing things that don't depend on who's looking. So we would get the same answer if we were on Mars or Montreal or, you know, Andromeda or somewhere else. We would agree between all different places about what makes an electron. And how do we do that? Well, we use two ways of labeling. One is called the mass. How heavy is a particle? So, for example, a particle of light, a photon, has no mass. But a mandaon has a mass of about 60 kilograms. You know. So that's one way of telling which kind of subatomic particle you've got. And another way is by asking, if it has a little spin to it, does it just sort of rotate all by itself and have a bit of angular momentum? If it spins around, how much spin has it got? And it turns out, surprisingly, that there's only, those are the two things that's enough. All you need to know to tell whether it's a particle, whether it's this kind of particle, that kind of particle, you just need to know its mass and its spin. So if you can measure how heavy it is, some way, and if you can measure how much it's spinning like a little spinning top, then you can work out what particle it is. And there's a convention in physics that people say if a little subatomic particle has a half a unit of spin, then it's called a matter particle. And if it has spin that's, instead of being a half of something, it's a whole thing, like it's a 0 or 1 or 2 or some other whole number, then those are called interaction transmitters, or otherwise known as force transmitter particles or bosons. And so physicists make this distinction between stuff, matter particles like electrons, and things that act on stuff, like light particles. So people will say, well, we can distinguish between matter, things like electrons and quarks, which make up the stuff of matter, and then we just separate off and talk about force as a separate idea. We say, well, we've got the matter, things like, you know, electrons and quarks and all the atoms and stuff in our bodies, and then after characterizing how much it weighs and whether it's got this little spin thing, we're interested in how it gets acted on by forces. For example, any two bodies, as Newton taught us, in the universe that have mass, get attracted gravitationally. So it wasn't, I don't know whether you're aware of this, but right now each of you is experiencing a gravitational attraction from me. And, You know, I'm actually attracted more strongly to people that are closer to me because of the laws of gravity. So this young woman here and I are attracted relatively strongly, whereas Justin and I at the back of the room are attracted relatively weakly by comparison. And how much we're attracted by that gravitational force is characterized by how heavy I am and how heavy the other person is. So the more heaviness we have between us, the stronger the force is going to be between us. And that's the way that the force of gravity works. Now, just so that you don't worry about all of a sudden ending up in a group hug in the middle of the room because of the force of gravity, the force of friction on your butts is more than strong enough to counteract that force of gravity, which is why we're not all ending up in a heap in the middle of the room. But you know, I mean, you sort of get the idea that there's a lot of stuff going on. If you think hard enough about it, you suddenly realize that even a room full of people has a lot of really interesting stuff going on. So, at any rate, what I was trying to point out here is that there are things called matter, which are electrons and the quarks that make up protons and neutrons inside the nucleus, stuff particles. We call those matter if we're feeling very sophisticated as physicists. And then once we know what the stuff is, like me and this lovely woman here, after we've determined how much we weigh, we're interested not only in whether we're stuff, but how we behave in relation to other stuff. And physicists call those interactions. And that's just fancy word for force. So physicists have this interesting idea, and I'm sorry to try to introduce so many concepts, but there's just so much to talk about because it's all so fascinating. Let me imagine now, let's strip away all the complexities of what we've been talking about for a while and just focus on these two people here, this young person and I. And we are both considered to be stuff particles, and we're going to play a role on an ice skating rink of a couple of electrons. Now you know that, just because of what you learned in school, that a couple of electrons, they're both minus charged, and so we ought to repel each other. So if physicists say that the force between a couple of electrons, that electric repulsion, can be represented by some particle physics, are they out of their minds? I mean, are they just on drugs? I mean, what are they smoking? I want some of that, So how do physicists imagine that particles can mediate the exchange of forces? Well, here's a thing. Now, suppose that this young lady and I, that was electron number 1 and electron number 2. Suppose I had in my possession a medicine ball. Now, you ever have to do PE class in high school where you had these really heavy balls and you had to do stuff with them to build muscles and things like that? I mean, boring. But they were pretty heavy. Now, so imagine that I have a medicine ball, and I'm going to call this the photon, or the particle of light, the particle that transmits the electric force and the magnetic force, and I'm going to treat this little medicine ball, I'm going to call it the photon. And now what I'm going to do is I'm going to throw it to this woman. So if I'm standing on ice skates and I throw the medicine ball, what's going to happen to me? Do I move? How do I move? Do I move in the same direction as the ball? The opposite direction? Opposite, right. So that's recoil. It's like if I fire a gun from a bullet. Sorry, a bullet from a gun. That just goes to show you that I'm not very good with guns. I was taught to shoot a handgun by a US Marine. I turned out to be quite a good shot, actually. Don't know what that should tell anybody. At any rate, what's just happened is that as I've thrown the photon, or the medicine ball, to this other electron, I've moved backwards. All right, so now let's fast forward the movie and look at what happens when she catches the photon, or she catches the medicine ball. If she was standing still on the ice, originally, and then she caught the ball, say the ball was moving in that direction, which way would she move when she caught the ball? She'd go backwards. She'd recoil as well. So, as you can see, if we both started out not moving, stationary on the ice, we're standing in a circle, and she's standing in a circle, and I'm standing in a circle, if we chuck this medicine ball back and forth a few times, that's called exchanging a photon particle in the lingo, then what's happening to us, the two electrons? We're moving apart. That's the representation of electric repulsion in particle physics terms. So that's how exchanging a particle, called a force messenger particle, or a force carrier particle, how exchanging a particle of light, called the photon, can lead to electric repulsion of a couple of electrons. So that's just sort of an intuitive description of how particle physicists think about force. You see, we're very simple creatures. We want to reduce it all to the simplest possible way of thinking about it. And what we learned is it's very useful to think about forces between stuff particles, otherwise known as matter to physicists, and to think about the forces between them as mediated by yet more particles. So we just learned how you could express electric repulsion between a couple of electrons in terms of exchange of a photon, which was played in our little play by the role of a medicine ball. So that's just an example of how the little ideas of particle physics and focusing on the physics of the very wee, you can learn quite a lot about how things work. So we learned that how do physicists tell particles apart by asking how much they spin, if anything, and how much they weigh, how heavy they were, and that was enough to characterize things. How do you characterize a force? Well, one of the things that we've discovered about the physics of the world, physics of the universe, the physics of the micro, the physics of the macro world, is that there are, fortunately, only 4 forces in the universe. The first one we discovered was gravity. That's the one that's keeping our butts securely parked on our chairs. The Earth, the big fat Earth, is pulling us gravitationally towards its center, and that's why we're, sitting quite nicely and feeling the force of gravity. If all of a sudden the Earth disappeared, which I admit isn't very likely, but if all of a sudden a magician were to go poof and make the Earth vanish, we would all start floating off into space. I mean, there wouldn't be anything pulling us down and keeping us on the face of the planet. So gravity, it's the oldest force that we've known about, and it's still my favorite. So what about the other forces? We've already talked about the electromagnetic force, and that's just a fancy word for the combination of electricity and magnetism. So that was the second force that humans discovered. As I mentioned, the force between a couple of objects that's an electromagnetic force is mediated by the photon. That little medicine ball that the two of us were chucking back and forth in our little ice skates experiment, that's the object that transmits the electromagnetic force. So you can be all sophisticated and say to your neighbour at the pub, well, I heard the other day that, there's no such thing as the electric force, there's just an exchange of photons. And that wouldn't be wrong. The gravity force is mediated by an exchange of gravitons. And the only difference between a graviton and a photon is that the graviton has 2 units of spin, whereas the photon's only got 1. And that's how we distinguish between those two things. And both the gravitational and the electromagnetic force are felt by quarks, and both forces are felt by things like electrons as well. And these forces are infinite range in the sense that the gravity force can reach out to the very edges of the universe. As I was talking about before when I was comparing my gravity attraction force of this woman here with Justin when he was at the back of the room, gravity is weaker the further away the two objects that are pulling on each other. But it does reach out to the very edges of the universe, even though it's very weak there. And the electric force also works over all ranges of distance. But the two nuclear forces, the strong nuclear force, the one that holds together the atomic nucleus with those gluons that I was discussing, that strong nuclear force only acts over very short distances, over distances of order the nuclear distance, which is about 1/millionth of a billionth of a meter. And inside the nucleus there's also another force, which is called the weak nuclear force. All you need to know about it is that it makes radioactivity happen. So it helps keep the lights on. So apart from talking about these 4 different kinds of forces, the gravity force, the electromagnetic force, and the nuclear forces, how do we tell the difference between different forces? And we said that mass and spin were the 2 things that characterized a stuff particle. What's the most important thing that characterizes a force? And that is how strong it is. So as I mentioned, gravity is a very weak force. The friction of your butt on the chair is more than enough to counteract that gravitational attraction between people in the room. So gravity is a very weak force. Electromagnetic force is somewhat weak. The weak nuclear force, as you might imagine, is somewhere in between them. And the strong nuclear force, surprisingly, is a very strong force. So we tell the difference between those different 4 forces by who they act on, over what range they work, and how strong they are. And the question that people ask themselves if they're wanting to come up with a description that talks about all of the forces and all of the particles under one rubric, you're going to have to talk about a lot of things. You're going to have to be able to make a theory or a description that's able to handle all of these different aspects. So it can be quite challenging. Let me just not try to motivate at a basic level why unification might be a reasonable thing to expect. Let me just say, if there are all these crazy ideas about how to put together forces in different ways and understand the basic structure of how particles interact with one another and so forth, how do we test these ideas? I mean, it's all very well to think about the structure of matter on very short distance scales, to worry about the physics of the microscopic. How do we check? How do we tell that what we're talking about is not just imagination, that it's real? The way we do it is by building what some people call atom smashers. and those of us in the business called particle accelerators. And what we try to do is, essentially, in a ring, we try to take a whole bunch of little subatomic particles, like electrons, or the current machine that we're building is called the Large Hadron Collider, and it accelerates protons. So what we do is we take a whole bunch of protons and we make them go really, really fast in one direction. So we spin them around and we apply some magnet fields so they go round and round in circles. And we get lots of them and lots of them, and we put them in little beams and we have them going round and round in circles. And you might think that this doesn't sound very interesting, and it isn't. But let's suppose inside the same set of tunnels, rings and stuff, and you can see some schematic diagrams here. By the way, the size of this experiment, this is several kilometers across. That's Lake Geneva back here, and the city of Geneva in the mountains. And this detector, which is one of the giant machines called Atlas, that's going into this structure, this is about the size of a human being. So it's about 44 meters across, this particular thing. So they're building these really, really, big-ass machine. It costing billions of dollars, and it's the frontier of research in particle physics across the whole world. There's a collaboration of over 70 countries worth of people, of order over 5,000 physicists, all working on constructing this giant, amazingly muscular atom smasher. And so I said that it has a beam of protons going whizzing around one way. Well, what they do is they make another beam of protons whizzing around the other way. They manage somehow to make the magnets all switch, and so that they can have them going whiz, 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 around clockwise, and another set going whiz, 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 anti-clockwise. And what they do is they have the magnets, they speed them up, make them go faster and faster, and then they arrange to make them crash into each other. And at those crashing into places, they put all this expensive kit and hardware and lots of computers and all sorts of really cool things. And to see what comes out of that fireball that results when you smash these teeny, teeny subatomic particles together, you slam them into each other at incredibly high energies. What you're trying to do in making that atom smasher is to bash a whole bunch of protons coming from one side, bash them into a whole bunch of protons coming from the other side. By the way, I would be able to show you bashing them into each other if I had 3 hands, but I'm trying to use the microphone. Let's see. So we have a bunch of counter-rotating beams of subatomic particles, and they're going round and round and round, and then we make them, wow, smash into each other. And the amount of energy that those things can be made to have when they smash into each other is quite amazing. And it makes all these amazing things and pretty pictures, and that's what all that expensive kit is there to do, is to look at that fireball, which will tell us, the idea is by bashing them together with higher and higher energies, by slamming them into each other with more and more muscular, speed, that we can dig deeper and deeper into the subatomic structure and learn about what they're really like at their very shortest distance scales. We're trying to peer into the heart of a subatomic particle by building this machine. And we're trying to peer into the heart of the subatomic particles, like the protons and the electrons and the quarks and everybody. But even more than that, we're hoping to discover new ones that we haven't seen, and that it could only be born inside a fireball that has enough energy to make these new particles. And so this is just one example of a very big experiment that's being built to check all these ideas. And it's sort of funny that in order to get down to the very shortest distance scales, to dig very deep inside the structure of matter and force, you have to bash things together with a lot of energy and you sort of slam them into each other as hard as you possibly can. And we would build a machine that was bigger and meaner than this if we could, but this machine is already pushing the boundaries of what's possible to build, even just at the level of designing computers and designing stuff that doesn't blow up when you bash stuff at it really hard. It has to be pretty tough stuff that you build this detector out of. And people from the University of Toronto are very involved in constructing this thing and moving towards finishing it. And this will turn on in a few months and start providing results, which is going to revolutionize the field. We hope to discover, for example, a particle called the Higgs at this new machine. How are you doing time-wise? Let's switch the tape. Sorry.